So we are going to start to look at three new parent functions today. Two of which really will be the main focus of the rest of the unit. The third one is just kind of like, I'd say, a cool thing to see, and we'll have to do some transformations with it. So remember, we saw that parent functions are pictures of the patterns that form as we do basic mathematical functions, like squaring numbers. When we square numbers, they stay positive and they grow faster than the numbers themselves. We get a parabola, right? Exponentials, when we raise a number to different powers. Absolute value makes things positive, which is why we get that V graph. So we've seen how the operations give us different shapes. So what we're going to do now is we are going to see if we graphed on a regular graph, not a unit circle graph, the Y value on the unit circle. So basically, the two things we're going to be following, our input is going to be the angle. Okay, so what's the angle, specifically in radians, and then the output is going to be the Y value on the unit circle. Now we know the Y value on the unit circle, if I draw a little picture here, could also be thought of as the sine of the angle. Okay, so really, when I say I'm graphing the Y value on the unit circle, I'm graphing sine. So we usually in a table will use our quadrantal angles for this because those are the most interesting points, although I have a table over here, so we're going to kind of see how the graph is shaped in between there too, just for this once. So what we do is we're going to use the points on the unit circle. So here's my angles. So if I'm at an angle of 0, that point on the unit circle is 1, 0. So the Y value, right, sine is Y on the unit circle, is 0. When I come up to pi over 2, the Y value is a 1. And this is something if you want to try to get the rest of it. So right here, I have negative 1, 0, so my Y value is 0. At 3 pi over 2, my Y value is a negative 1. And here, I have a 0. So I'm going to graph this out. Now, this is brand new and definitely something you'll want to watch. When we graph, first off, I see I want my angles from negative pi to 3 pi. My table only goes from 0 to 2 pi. So I'm going to put my axes here. So my y-axis is basically in this spot where it's a little bit more towards the left. So when we do scales, depending on transformations, we'll could have different scales on the x-axis, but in general, I'm going to do every 2 spaces is a pi over 2. So I'm taking those angles and then putting them along the x-axis because they are my inputs. For the y-axis, usually it's fine just to leave by points. So graphing these points out, I have my first point is 0, 0. My second point is pi over 2, 1. And then I have pi 0, 3 pi over 2, negative 1, and 2 pi. Now, the question is, does this graph like go straight, like almost like this? I don't want to draw it because I'm going to have to erase stuff. So, does it go like that? Does it go like this? Like, does it go like this? Like, what type of shape do I get as I connect those points? So looking at a little more specific values between, so we're going to zoom in and see what's happening between 0 and pi over 2. So looking at these numbers, this is just from our table. The sine of pi over 6 is 1/2. The sine of pi over 4 is radical 2 over 2. And this is radical 3 over 2. And we know this is a 1. Okay, so we have the 0 and the 1. Now, this is not super helpful for me. Because I don't really even know where radical 2 over 2 is, but if I do decimals for each of these, so if I type square root of 2 over 2 in my calculator, I get 0.7, and square root of 3 over 2 is like 0.8660, but for graphing purposes, we're going to round to 0.9. So if I put these numbers in, first off, if I start here, I'm already at 0.7 by the time I'm halfway to pi over 2. Pi over 6 would be about here, that's a 0.5, and pi over 3 would be about there. So I do see that this graph has a bend to it, okay? So it doesn't just go straight up to that point, it has a bend. Now, using reference angles, if I come back down the other side of the unit circle, it's gonna bend again. And then this bend is gonna continue. So we could also look more specifically at that, but that is enough to kind of see what it's doing. So we wanna continue this graph, so that piece that I'm looking at, the blue piece, is the graph of sine. But we know from coterminal angles, we can keep going around the circle and the pattern will repeat. So if I continue this out to 3 pi, this would be 5 pi over 2 in here. And going back to negative pi, I'll see that this pattern just keeps repeating because being at negative pi over 2 is the same angle coterminally with 3 pi over 2. And the same thing in this direction. So we get this kind of wave pattern that would continue on forever. So now that we have this parent function, we're going to answer questions about it. So the first one says, what is the y-intercept of sine theta? So we can see the y-intercept is 0. The maximum and minimum values, that's our y values when we ask that question, right, are 1 and negative 1. And then here are 3 new vocabulary words that we use when we talk about trig graphs. So the first one, because these graphs have kind of these patterns, they're contained, they don't go to infinity in the y direction, we have a midline. So that's the line that is in the middle of where this wave is happening. So in this case, we haven't done anything fancy, so our midline is just y equals 0 or the x-axis. The next word we have is something called the amplitude, and the amplitude you can think of as the height of the graph. Now height could mean 2 things. The height here means the height from the midline to the max. So not from the bottom to the top, from the middle to the top. So the amplitude is a 1. Because these graphs repeat, we talk about their period or how long it takes to do one cycle. So if I trace this out, I finish one cycle between 0 and 2 pi is one spot I can look at it. So that has a length of 2 pi. This is going way back. Do we think this is an odd, an even, or neither graph? So basically an even graph would be symmetric over the y-axis. An odd graph, if I rotated about the origin 180, it would end up being the same. And that is true here. If I rotate sine 180 degrees, I do end up on top of itself. So this is an odd graph. We could explain that. Another fact we learned about a negative angle, in the last unit, we said the sine of a negative angle is the same as the negative sine of the angle. And way back in unit 5, we learned that this fact is true for odd graphs. So that's another way we could show that sine is an odd function.